Hello everyone, welcome back to Electronics 1. Following up on a figure we looked at in the last lecture, here we saw the output characteristic of our MOSFET, and we see that there's two distinct regions, and I guess a third region if we talk about cutoff. And we saw the equation that defines the all regions of operation of our MOSFET. Let's dig into that a little further, and let's explore a little bit more specifically in the triode region. So if we look at the triode region and look at our general form of the equation, so the textbook uses this Kn prime term. That Kn prime is made up of a term that's the capacitance per unit area and the electron mobility. Okay, so this is a constant that the textbook defines as Kn prime. Okay, this Kn prime term is called the process transconductance parameter. Process transconductance parameter, and the term, the process, means that it's a function of the process technology that's used to fabricate our MOSFET. Okay, and we refer to it as a transconductance because the electron mobility and the our oxide capacitance has an impact on the channel conductance. Okay, so this term here is our oxide capacitance per unit area, and therefore has units of farads per meter squared. This term is, as I said, the electron mobility, and has units of meters squared per volts seconds. Oops, this second should be on the bottom here. And the total Kn prime, our process transconductance parameter, has units of amps per volt squared. Okay, so that is multiplied by our aspect ratio of our transistor, and it is just exactly how it looks. It's a function of the width of the channel and the length of the channel of the MOSFET, and that times our overdrive voltage minus the drain to source voltage, or half of the drain to source voltage. Let me go and actually multiply the drain to source term into our expression here. So up here they've kept the drain to source term. They've just factored it out. Let me put it into the equation. So I've got my drain to source squared over 2. Okay, And just a reminder again that this overdrive voltage is my gate to source voltage minus my threshold voltage. Okay, so in the triode region, so if we specifically focus on this region where values of VDS are small, and if we look at how that impacts our the equation, and again this is the general form of the equation, we can make some simplifications to that equation. Okay, so if we look at what happens and how we can simplify that equation for small values of VDS, right? So if the VDS term is small, particularly if it's small relative to our overdrive voltage, then this term here can be ignored. Okay, a small term squared is just going to make the term even smaller. Okay, so assuming it's fractional, I suppose. So VDS squared can be ignored for small values of VDS. So that means that our equation here, this equation up here, if we ignore that term in the equation, we end up with an expression for the drain current that's our process transconductance times my aspect ratio, or my width divided by my length, times my overdrive voltage times VDS. Okay, so for a given gate to source voltage, this term is going to stay constant, and therefore we have a linear relationship between the drain to source voltage and the drain current. In fact, we could go one step further, and let me bring this drain to source voltage over to the left hand side of the equation. And I note that while I have the current through the device divided by the voltage across the device, well, that's a conductance, or 1 over a resistance. Okay, so this is that region that we explored, that linear region of operation down here, so for low values of VDS. That is the reason why we can assume linearity in that region, and that's that region where we can use it like a voltage controlled resistor. Okay, so again, for low, and this does not cover the entire triode region. This simplification applies only to low levels of VDS, right? So down here where VDS is low, and we can assume that it's negligible in our general form of our equation. Okay, let's talk about the saturation region of our operation now. So if we look at the saturation region, and if we have a look once again at the general form of our equation, I'm gonna write this out just to remind you what it's made up of. Oops. We'll even sometimes see this this whole term written as a transconductance parameter Kn. Okay. This is rather than just a process transconductance. This is known as transconductance parameter. Okay, so if you're given a value of Kn prime, it's just referring to the electron mobility times the capacitance, the oxide capacitance. But if you're given a value of Kn, which is the transconductance parameter, it represents this whole term here shown. Okay, so our expression was our overvoltage times the drain to source voltage minus the drain to source voltage squared divided by 2. Okay, but we said at saturation, or at least at the edge of saturation, so for saturation we said the drain current is constant once VDS is equal to the overdrive voltage, which is our gate to source voltage minus our threshold voltage. Okay, that's where pinch off occurs and our drain current becomes constant. Okay, and we're going to look specifically at kind of the edge of saturation, but if you have a look at the text, you will see that as the drain to source voltage exceeds this value where it's actually equal to the overdrive voltage, the current still remains constant, since any drain to source voltage beyond the overdrive voltage, that additional voltage drop just gets dropped across the depletion region. There's a bit of a description of that in the text if you want to dig into that further. So we'll look at just the case where the drain to source voltage, where it just becomes equal to the overdrive voltage. In fact, this point at the edge of saturation, this is in fact known as VD. The textbook refers to this as VDS sat. Okay, so I'm going to just leave that out of there for a second. And if we take and substitute in then everywhere, so if VDS is equal to the overdrive voltage at this region of interest, well then we can just take the overdrive voltage and substitute in to this equation in both places where we have the drain to source voltage. Okay, so my expression, I'm just going to use Kn now here, becomes the overdrive voltage times the overdrive voltage minus the overdrive voltage squared divided by 2. Okay, of course this becomes the overdrive voltage squared minus 1/2 of the square of the overdrive voltage, or becomes just equal to half the overdrive voltage. So I'm just going to pull this term out and we get an expression for the drain current that is now constant and independent of the drain to source voltage. Okay, and again, just remember that Kn term, the transconductance parameter, is my electron mobility times my oxide capacitance times my aspect ratio, or my width, divided by my length. So this is the same expression, just with the transconductance parameter written out, or the underlying aspects of the transconductance parameter written out. Okay, so here we see that the drain current is no longer a function of the drain to source voltage, is constant and independent of any change in VDS. Okay, so purely a function of my overdrive voltage, or my gate to source minus my threshold voltage at this point. Okay, and again, that's this region here on the characteristic where it's flat, where, as stated, the drain current is no longer dependent on the drain to source voltage. Now again, you might think, well, as the drain to source voltage increases, this simplification I made here no longer applies, but the additional drain to source voltage, so it gets dropped across the depletion region, so effectively the drain to source voltage saturates, and that's why we call it VDS sat. So this mode of operation, this saturation mode of operation, as stated before, that's the mode, and it's a bit confusing after talking about BJTs, but that's where the MOSFET is operated as an amplifier. And as can be appreciated from our expression here, the drain current is independent of the voltage drop across the drain to source. It's purely dependent on our gate to source, or our overdrive voltage, and effectively the MOSFET becomes a voltage controlled current source, right? Which is exactly how we described the MOSFETs in way back in the beginning. And if we want to, looking at figure 5.14 of Cedra-Smith, here's a plot that actually relates the operation, or has to look at the operation in saturation mode. So here we see that how that gate to source voltage impacts the drain current simply through this this expression that's shown here. Okay, so this would be the MOSFET equivalent to looking at our relationship between for a BJT between the base to emitter voltage and our collector current. Okay. Describing this operation through the use of a model, again pulling figure 5.15 from Cedra-Smith. Here's the large signal model of the MOSFET operating in the saturation region, operating as a amplifier, a voltage controlled current source. And we see these relationships that we talked about above here being depicted, this current being a function of the square of the overdrive voltage. We will explore the small signal operation of the MOSFET briefly in a couple of classes. Okay, so if we look at figure 5.13, this describes the entire output characteristic of our MOSFET, shows all of our regions of operation. We see our all of our modes of operation. We see our cutoff mode where the gate to source voltage is below the threshold voltage, right? So we have no current flowing. We see the triode region shown here, where the drain to source voltage is below the overdrive voltage, and we operate in this triode region. For low values of drain to source voltage, we have linear operation, but as the drain to source voltage increases, we get tapering of the channel, and that tapering of the channel is depicted on this diagram by a rounding off of the relationship between the drain to source voltage and the drain current, right? It starts to become nonlinear. Then we reach this region that's the point where the channel pinches off. That occurs when the drain to source voltage equals our overdrive voltage, right? That pinch off point can be described by this equation. You see it's a parabolic equation. We see it's a squared relationship. The square of the current at that point becomes a function of the square of the drain to source voltage. Okay, and from that point on, beyond pinch off, the drain current dependent on the gate to source voltage, but no longer dependent on the drain to source voltage. Okay, so our input gate signal will control the magnitude of the drain current, but the voltage drop across the device drain to source will no longer have an impact on the drain current, right? So we get constant current operation. Okay, or do we? Well, and we're going to look into an effect on our MOSFET similar to the early effect that we saw in our BJTs, and we'll come to that in the next lecture. So if we compare this to operation of a BJT, I'm just going to make this a little bit smaller here so I can show both at the same time. Here in this operation that I've shown here for the BJT shows the early effect, but if we ignore that for a minute and we see that the kind of a similar shape, we see the contrast in how the saturation region of our BJT differs from the saturation region of our MOSFET, right? It's the active region of our BJT where we have that constant current operation. Again, if we assume that these are in fact flat here and ignore the early effect for a second, right? And it's down in this region where we use the device like a switch that's on, and now we notice that one distinct difference is in the saturation region of our BJT. We see very high levels of conductance, not much resistivity, whereas in our triode region of our MOSFET, we really control the slope of that resistance, control the level of the resistance through the applied gate to source voltage. Okay, so just if we summarize here briefly, our MOSFET, the output current is controlled by VGS, my gate to source voltage, my mode delimitation variable, that thing that determines which mode I'm in for my MOSFET, is when I reach the pinch off voltage, which is when the drain to source voltage equals my overdrive voltage. So that determines when I switch between triodes region of operation and the saturation region. And finally, still applied to the MOSFET here, in saturation mode, saturation mode device has constant current, and this is where it's going to act like an amplifier. Okay, and again, that's a key thing to remember, not confuse, because in our BJT we call saturation mode that region where it acts like a switch, an on switch. Okay, so for our BJT, our output current is linearly controlled by the base current. Okay, you may say, well, it is a function of VBE, and which is actually what's depicted on this diagram here. But as VBE increases, so does the current IB, right? So you can kind of look at it from either perspective. We often like to look at it as a current controlled device because that relationship is linear, where the voltage control is non-linear due to that PN junction. That mode delimitation constant, and it's essentially constant in our BJT, is the collector to emitter voltage when it's equal to VCE sat or below. That is the point where we switch between the saturation region. This isn't well depicted on this diagram, but that VCE sat is approximately 0.2 volts, and that's why we've called it a constant here. So it's that constant value of collector to emitter voltage that when we fall below it, we're in saturation region. If we go above it, we end up in the active region. Okay, and finally, it's not saturation region where we have constant current, but it's that forward active region. Where the device is, or I should say has, constant, my tablet here is struggling to keep up, constant current. And I meant up here to say as well constant current up here as well. I left the word current off. Okay, so said it's forward active region for a BJT where it acts like an amplifier. Okay, so in many ways, and if we look at the output characteristic, the voltage across the device versus the current through it, we see similarities. The naming convention's a little different, and very different because the saturation region in our MOSFET refers to the mode where it operates as an amplifier, where the saturation region for our BJT is that mode where it's acting like a simply like an on switch. Okay, so what we'll explore in the next lecture is similar to the early effect that we see with BJTs, and that base width modulation. We're going to see a similar effect with our MOSFETs, and it's known as channel length modulation. So we'll explore that effect